In this short video, I'm going to go over a couple of different perspectives on how to predict the effects of harvesting a population. That is, deliberately increasing the death rate in order to produce some, as a byproduct of increasing the death rate, we produce something of value in terms of the number of animals or carcasses. Beginning of the 19th century, lynx were widespread throughout Norway. But as human populations grew, so did negative interactions with lynx. And in the middle of the 19th century, the government issued a bounty on lynx, essentially paying for dead lynx, which remained in place until 1980. Throughout that period, the allowed methods for taking lynx were reduced and populations recovered somewhat from their lowest levels in the 1940s. However, by 1976, lynx were restricted to just two small remnant populations and were listed on the CITES Appendix 2. After the bounty was removed, hunting was still allowed. The season was restricted starting in 1982, but there were no restrictions on the number of lynx taken. Lynx populations again began to recover according to records of the number of lynx harvested. Throughout the 1980s and early 1990s, the number of lynx taken annually was less than 50. In 1992, there was some public outcry because a mother and both of her kittens were harvested by a hunter, which temporarily led to the cessation of all hunting. And in 1994, a regulated harvest with a restricted season and a nationwide quota of 47 animals was allowed. That's the beginning of the graph you can see right here. In addition, a program that compensated livestock owners for losses to lynx and other large carnivores was put in place. Population size of lynx has been estimated using consistent methods since 1996. That's the start of this curve here. Quotas were greater than 25 to 30% of the estimated population size, and populations declined steadily until 2004. Since 2004, quotas have been kept at less than 20% of the estimated population size, and as you can see, numbers of individuals continue to increase. I'm going to keep some of this in mind as we go through some discussions of just how we go about regulating the harvest of wildlife. You've probably already heard of the concept of compensatory mortality. It's widely attributed to wildlife populations that are harvested for recreational or sport purposes. The basic idea is what is the relationship between additional anthropogenic mortality, that is harvest mortality, and the survival probability of an individual. So what we have here is increasing anthropogenic mortality and individual survival probability. When there's no anthropogenic mortality, individuals are going to have some survival probability. It will be less than 1 because there's a natural probability of death. If harvest mortality or anthropogenic mortality is not compensatory, then as you add anthropogenic mortality, the individual probability of survival decreases and eventually will reach 0. If this is the case, then what you would expect is that any increase in harvest mortality will decrease population sizes and potentially be able to overwhelm natural variation in survival and birth rates and perhaps drive populations to extinction. So additive mortality is considered to be bad. The compensatory mortality hypothesis, on the other hand, suggests that as anthropogenic mortality increases, the individual survival probability, does not decrease. In fact, it remains constant. And the reason for this is that goes back to the notion in the early part of the 20th century of the doomed surplus. By removing individuals through harvest, we're leaving the remaining individuals more resources to get through particular crunch periods such as wintertime or other periods of a shortage of resources. And as a result, their individual survival probabilities don't decrease up until some particular point at which we exhaust the capacity of the population to compensate for the added mortality, and then individual survival probability does begin to decrease. You can see that if the compensatory mortality hypothesis is true, then essentially harvest in this region here, between 0 and this compensation point, is going to have no impact on the population dynamics at all. This is the basis under which most wildlife populations have been harvested, or the justification for the harvest of most wildlife populations, game populations, since the early 20th century. The basic issue with the compensatory mortality hypothesis is that, as we've seen in previous sections of the course, as the density of individuals in a population changes due to harvest or any other component, there's a number of ways in which the life history can respond. It could be that the relationship between survival and density is flat, and there is no change as you reduce the density. All of the regulation in that case comes about through changes in the birth rate, or alternatively could be both the birth rate and the death rate. So the compensatory mortality hypothesis is a rather restrictive way to view the effects of a harvest on population size. And what we're going to do instead is focus on logistic population growth and then adding harvest to it. So what we have in this curve is the basic quadratic relationship between the population growth rate and population size. When populations are small, the growth rate increases, reaches a maximum at half of the carrying capacity, and then it declines until it reaches the carrying capacity. This carrying capacity here is an equilibrium point. Above the carrying capacity, the population growth rate will be negative. Below the carrying capacity, the growth rate is positive, and so populations will tend towards this point here. And we get this curve. This is not per capita growth rate now. This is actual change in population size. We get this curve from our two per capita lines, per capita birth and death rates, right? And K is where those two are equal. What we're going to do now is say what we want to do is subtract from our population growth rate, or population change, is some harvest rate, little h, times the population size. So little h is a constant rate of harvest, per capita rate of harvest, and so the actual harvest then increases as a straight line, h times n now, increases as a straight line. If we double the harvest rate, we get a steeper line. And what we would find in this case is that we actually get new equilibrium points, right? So if h is here, we're going to have a point at which the number of individuals removed by the harvest is equal to the number of individuals being added through population growth. And we're going to get a new equilibrium point here. Double the harvest rate, we get another equilibrium point here. The key point, though, is that in both cases, the new equilibrium point is less than the carrying capacity K. You can imagine continuing to increase this harvest rate, and this line is going to keep rotating around. It's always going to have an intercept of 0, because in the population is 0, there's no harvest. But eventually, if this line continues to get steeper and steeper and steeper, it will go entirely above the population growth rate curve. And that happens when our per capita rate of change, h, is greater than the intrinsic rate of increase, little r, which is the slope of this curve right at the intercept. And at that point, there will be no equilibrium point. Our population, in fact, will be completely, our harvest is exceeding the capacity of the population to replace itself, and we will drive the population to extinction. So here's our basic discrete time logistic growth model. This is actually a form called that in the fisheries literature you'll see called the Shaffer surplus production model. We've got our population size next year is equal to the population size this year, plus some function of population size, which is where the extra growth comes in. So we've got the extra growth is our current population size times the intrinsic rate of growth, and then it's multiplied by the same factor, 1 minus n of t over k, the carrying capacity. That much is basically our logistic population growth. But what we're going to do now is, in addition to that, we're going to subtract some amount of harvest. And that harvest is going to be our per capita harvest rate, little h, times the population size. And what we want to know is, at the new equilibrium point that's been created, how many individuals are harvested? We're going to call that big H. So the first thing we have to do is work out what is the population size at our new equilibrium point. And we do that by asking if n at t plus 1 is equal to n at t. So we just set that, call that n star, write n star throughout this whole thing, and then solve this equation for n star. Without the harvest rate, we know that the answer we're going to get in that case is simply n star equal to k. Ignore the star there. The carrying capacity, right? In the absence of harvest, our population will come to an equilibrium at the carrying capacity. Once we add this harvest, we end up with this new term, which is basically 1 minus little h over r. And that's going to be the ratio of the harvest rate to the intrinsic rate of growth. That will be the equilibrium that we come to. So you can see, remember, if little h is bigger than little r, then this piece here is going to be bigger than 1, and our equilibrium population size will be negative, which is clearly not biologically realistic. That reflects the fact that a harvest rate greater than the intrinsic rate of growth of the population will drive the population extinct. Once we've got n star calculated this way, we can sort of plug that in and ask, okay, if we have this thing n star here times h, how many? That'll be h star, the number of individuals harvested at equilibrium. So that's this number here, simply h times k times 1 minus h over r. So what does that look like as a graph? On the left here, I've got the same graph I showed you before. Population rate of change on the y-axis, population size on this axis down here. And the dashed line shows you the effect of a given harvest rate, h. So as h gets larger, little h gets larger, this dashed line rotates upwards. Here's our equilibrium population size right at that point. What I want to do now is plot out, okay, how does that total harvest, h star, change as I change little h? Assuming our population is starting out at the carrying capacity when we're down here at h equals 0, and then settling to some new equilibrium as I increase harvest. And it also has a quadratic form. As you increase h initially, the total harvest increases. That's logical. And this corresponding thing is happening is population size is decreasing. Total harvest continues to increase until you reach a peak on that curve. And that peak on there corresponds to the harvest rate that exactly matches the peak on the population rate of change curve. If you keep going past that point, continue to increase h. Now this dashed line is now intersecting our population rate of change curve on the on the left-hand side of the peak, and population size continues to go down, but so does total harvest. And the reason is because now we're pushing the population downwards below its peak productivity. Now it's being limited by not by competition, but rather by a lack of individuals for reproduction. In the fisheries literature, populations that are on this side of the curve are referred to as overexploited because they are actually at a population size at which there's the same population size you can get over on this side of the curve and the same degree of harvest, but the population size itself is much, much smaller. Right? So we would rather be over on this side of the curve than over here. We're getting the same harvest, but over here we're just that much closer to extinction. Give this point on the top of this curve here a special name. It is called the maximum sustainable yield, or MSY. So maximum sustained yield, or MSY, is the harvest that is achieved when the per capita harvest rate is at a value of little r over 2. So we obtain this expression h equals r over 2 by looking at that curve and figuring out which value of h gives us the peak of the h star curve. And if you recall, the h star is this little h times n, and we know that at the peak n is going to be k over 2. So if we plug in little h, then our harvest is going to be r times k divided by 4. This is the maximum amount we can expect to yield from a population that is growing logistically and have it maintain its population size over time. Harvest rates that are either greater or less than this will cause us to have a lower harvest yield, total yield. Managing for maximum sustained yield was a basic concept for a lot of commercial oceanic fisheries for most of the 20th century. And you may or may not be aware, but the record of our management of oceanic fisheries is pretty awful. And for the most part, by the end of the 20th century, the vast majority of fisheries were heavily overexploited or even completely collapsed. That is to say, there was no longer possible to get economically viable yields. Peter Larkin, a fisheries biologist, penned this epitaph for MSY in 1977. Here lies the concept MSY. It advocated yields too high and didn't spell out how to slice the pie. We bury it with the best of wishes, especially on behalf of fishes. We don't know yet what will take its place, but we hope it's as good for the human race. The basic problem with MSY is that it assumes too much knowledge on the part of our management. If you've got accurate estimates of little r, k, and population size, you can target that maximum sustainable yield, except that by now you should be aware that we are almost never going to have highly accurate information, so targeting MSY takes us much, much too high. We should regard it as an absolute maximum limit to be avoided at all costs rather than a target. Besides harvesting a constant proportion of the population, there are other ways we could choose to manage the harvest. One approach, common approach, is to use what's called a fixed quota, some number of individuals that will be harvested at each time period. Go back to our plot of population growth rate against population size. A fixed quota is a flat line now because we're going to aim to harvest that many individuals irrespective of what the population size actually is. Just like with a fixed proportion, we get a new carrying capacity that's lower than the unharvested carrying capacity. And you can see that if population size is pushed below, our population growth rate is above the harvest rate, the population should increase. If the population finds itself above that point, then the population growth rate is below our harvest rate and the population will decrease. So this is a stable equilibrium point. On the other side, we get another equilibrium point, a point at which the population growth rate and the harvest rates are equal. But this one is very different from previous equilibrium points. This is an unstable equilibrium. You can see that if we push this population away from the equilibrium point to larger population sizes, the population growth rate is larger than the number of individuals harvested. That means the population is going to increase. And so if we push if our population ends up at this equilibrium point, there's going to be pressure, growth by the population, to move up this axis to this equilibrium point over here. So that's good. But what's not so good is if we find ourselves on the far side of this equilibrium point over here, then the harvest is going to be larger than the population growth rate, and the population collapses towards zero. This is the issue with having fixed quotas and aiming for MSY. If we try to aim for an MSY yield with a fixed quota system, what that means is we're going to move this line here up until it gets as close as we can get it to this peak. But once it's there, you can see that any stochasticity in the system or errors in our measurement or almost many different features can push us down onto this side, and then we're going to be beyond the stable equilibrium and the population will collapse. In fact, with a fixed quota, it's possible to push the quota high enough, this dashed line up here, for example, where the harvest rate is higher than the population growth rate for all population sizes. And then in this case, the only equilibrium is extinction. So by pushing the fixed quota harvest to greater than the MSY harvest, that is R times K divided by 4, you can drive a population extinct. So which of these two options, fixed proportion or fixed quota, is safer from the perspective of avoiding overharvest and collapse of a population? Both of them rely on good estimates of population size. You can't really decide how many individuals to harvest in a fixed proportion harvest unless you also know what the population size is. As long as your estimate is accurate, the fixed proportion harvest is less likely to lead to an overharvest if the estimate is accurate. And that's because by harvesting a fixed proportion, as population size declines, say due to environmental stochasticity, then your harvest automatically declines and allows the population to recover. Whereas a fixed quota doesn't do that. One way that's sort of avoids some of the issues about relying on population size is to control the amount of harvest effort instead of the actual harvest rate. And the usual assumption here is that our harvest rate, H, is equal to effort, measured in whatever units you might have, times a catchability coefficient, or a harvest coefficient, Q, which basically translates an effort of a harvester per day, say, into the harvest rate. And so the more effort, the greater the harvest rate, and then that is then multiplied by population size. So you can see that as long as you keep effort constant, this means that as population size declines, you will be in a fixed proportion harvest, and everything will be rosy. You may not know exactly what that proportion is, but you know that it's not increasing. So that's substantially safer than the fixed quota, and also can be more reliable than the fixed proportion. The main issue with this kind of approach is figuring out what units to measure E in, and making sure that those units don't drift over time. Here's a really neat little example of the effect of effort on harvest and how it can shift over time. This is the statewide harvest of cougars in the state of Oregon. Prior to 1970, there was a period where they were entirely protected, following a bounty, much like the Norwegian lynx. And harvest sort of increased for a period of time, and then there were a few changes in regulations. But in 1994, the big change in regulations was a ballot initiative that led to the passage of a law that basically eliminated the use of dogs for tracking mountain lions for the purpose of sport harvest. What that meant was that now a mountain lion license was actually, it was much less likely to lead to a successful hunt because you had to track them down without the help of dogs. And you can see what happened in the few years immediately following the ballot initiative. The harvest rate plummeted to a quarter of what it had been prior to the ballot initiative. In 1998, the Oregon Department of Fisheries and Wildlife responded by changing how they issued mountain lion licenses. Previously, you had to purchase a specific mountain lion license. In 1998, it became possible to everybody who purchased a package of licenses that included licenses for elk and deer and other abundant wildlife, also automatically, at no extra cost, included a cougar license. What that meant was that now there were thousands and thousands of people on the landscape who were not, in fact, specifically targeting mountain lions, but who were able to take one if they came across one. And harvest rates jumped back up again and then continued to rise quite dramatically in the early 2000s. So one of the questions in here, a number of the people who were purchasing these so-called sport packs also rose during this period. So the question is this rise in the observed harvest, is this due to a change in the effort because there's more people who can harvest a mountain lion, or is it due to an increase in the population size? That's a sort of an open question at this point. What about additive harvest mortality? Is there a way to incorporate that into our current model? Well, with the logistic population model of wildlife harvest, the only way in which you're going to find additive harvest, that is harvest mortality that's not compensated by an increase in birth rates or a decrease in death rates, is if you've got exponential growth. So in exponential growth, we've got per capita birth rates are flat and death rates are flat with respect to population size, and say so is harvest. Harvest is a constant. Per capita harvest rate is a constant as well. So you can see then that the death rate and the harvest then add on to each other. But as long as they're lower than the birth rate, you're still going to have an exponentially growing population. So you can imagine looking at this now by, if you multiply these curves by population size, then what you're going to get is a population growth rate that increases with population size. And you can have a harvest that's either less than the net rate of growth or greater than the net rate of growth. If it's less than, population will continue to grow exponentially. If it's greater than, population will decay exponentially because now the death rate is greater than the birth rate. The only thing that would keep you constant would be a harvest rate exactly equal to the difference between birth and death rates, and that's extremely difficult to maintain. So what this suggests is that mortality or harvest mortality really does rely very strongly on the presence of some kind of density-dependent compensation in birth rates, death rates, or both.